Non-contact forces. Section 1. Electrostatic force. All matter is made up of particles called atoms. The nucleus of an atom contains positively charged particles called protons and neutrally charged particles called neutrons. The neutral particles have no charge. The nucleus is surrounded by negatively charged particles called electrons. Charged particles exert forces on each other. Particles that are oppositely charged have an attractive force between them. A positively charged proton will attract, or pull, a negatively charged electron towards itself. Particles that have the same charge have a repulsive force between them. An electron will repel or push away another electron. A proton will push away another proton. One way to remember this is that when it comes to charge, opposites attract. The image that follows shows an illustration of pushes and pulls that particles can exert. The identically charged particles push away from each other, while the positively and negatively charged particles are pulled towards each other. Like charges repel, and opposite charges attract. When objects made of certain materials are rubbed together, negatively charged electrons can be transferred from one object to the other. When this happens, the second object has an overall negative charge, and the original object has an overall positive charge. As a result, the two objects will be attracted to each other. For example, when you rub a balloon on your hair, the balloon becomes negatively charged, and the hair becomes positively charged. The hair is then attracted to the balloon. When a negatively charged balloon is brought near an insulating material such as wood in a wall, the molecules in the wall become polarized. This causes the particles in the wall to arrange themselves in a way that makes the surface of the wall positively charged. As a result, the balloon is attracted to the wall. Scientists explain electrostatic forces using an idea called an electric field. Any charged particles creates an electric field. You can think of this field as a three-dimensional, invisible set of lines that meet at the particle. In addition, if a charged particle is in another particle's electric field, it feels a force because of the electric field, and that force can affect its motion, just like any force. That is, an electric field allows a charged particle to exert force on another charged particle without touching the other particle. An electric field, like any vector, has both a magnitude and a direction. Electric fields can be represented by arrows. The arrows point towards a negative charge and away from a positive charge. Field around a negatively charged particle. Field around a positively charged particle. When two charged particles interact, they can either attract or repel. This can be modeled by showing the field lines around each particle. Notice that for the oppositely charged particles, the arrows point from the positive charge toward the negative charge. Opposite charges attract. Like charges repel. The strength of an electrostatic force depends on the amount of electric charge and the distance between the charges. When the amount of charge increases, the force increases. When the amount of charge decreases, the force decreases. The strength of the electrostatic force also increases when the distance between the charges decreases. This happens whether the force is attractive or repulsive. Summary. Electric charge is a property of particles that causes them to attract or repel each other without touching. Particles that have opposite charges attract each other. Particles that have like charges repel each other. The force of attraction or repulsion is called electrostatic force. An electric field surrounds a charged particle and helps us explain electrostatic force. If you have two or more charged particles, they interact with their electric fields, which causes the particles to attract or repel. The strength of an electrostatic force depends on the amount of electric charge and the distance between the charges. When the amount of charge is increased, the force is increased. When the amount of charge is decreased, the force is decreased. The strength of the electrostatic force also increases when the distance between the charges decreases. Stop and check. What happens when two like charges move toward each other? What happens when two opposite charges move toward each other? What are two ways electrostatic force can be increased? When one particle exerts force on another particle, the particles do not touch. How do the particles interact? Section 2. Magnetic force. Magnets are objects made of certain materials such as iron, nickel, or cobalt, and other metals. Magnets can exert forces on other magnets and objects that contain metals such as iron, nickel, or cobalt. In the Engage and Explore lessons, you used bar magnets. The bar magnets were labeled with an N for North Pole and an S for South Pole. If you cut one of those magnets in half, both halves would have a north and a south pole. If you cut the half magnets in half again, all the pieces will have a north and a south pole. All magnets, whatever their shape, have a north and south pole. Magnetic forces are similar to electrostatic forces because magnets exert force on objects without touching. Magnetic forces are also both attractive and repulsive. When like poles of a magnet are brought closer together, the force is repulsive. If you bring the two north poles of a magnet together, the magnets repel each other. If you bring the two south poles of a magnet together, the magnets repel each other. When opposite poles of a magnet are brought together, the magnets attract each other. As with electric charges, magnets can exert forces over objects without touching because of the three-dimensional magnetic field surrounding them. You explored evidence of magnetic fields when you investigated with tiny pieces of iron called iron filings. If you sprinkle iron filings around a magnet, the tiny iron pieces align with the magnetic field of the magnet. This allows you to see that the magnetic field lines curve from the North Pole to the South Pole. The lines of the field are closer together near the poles than at the center of the magnet. There are more iron filings near the poles because the strength of the magnetic field is stronger near the poles. Iron filings aligned along magnetic field lines. When two magnets are brought close together, their magnetic fields interact. You can see how they interact in the images. The lines of force from like poles repel each other. Just like with electric fields, you can show the lines of the magnetic field with arrows. When you try to push the like poles of a magnet together, it gets harder to push as they get closer together. The strength of the magnetic field is stronger at the poles and increases when the distance between the magnets is decreased. Iron filings around magnets with like poles near each other. Diagram of the magnetic field with like poles near each other. When you try to push the opposite poles of a magnet together, the force gets stronger as they move closer together. Again, the strength of the magnetic field is stronger at the poles and increases when the distance between the magnets is decreased. Iron filings around magnets with opposite poles near each other. Diagram of the magnetic field with opposite poles near each other. Magnets made of different materials can have stronger or weaker magnetic fields. For example, a magnet made of neodymium, iron, and boron metals is one of the strongest magnets that you can buy commercially. The magnets you often use at home or at school are usually made of blends of aluminum, nickel, and cobalt, and are not usually as strong as neodymium magnets. The strength of a magnet also depends on its size. When comparing two magnets made of the same material, the larger magnet will have a stronger magnetic field. Whatever type of magnet you have, the strength of the magnetic field is always strongest near the poles and decreases as the distance from the magnet increases. Because the outer core of Earth contains hot, moving, liquid iron, Earth itself behaves like a giant magnet. The Earth's magnetic field surrounds the planet. What can be confusing is that the magnetic south pole of Earth is actually located near the geographic north pole. So a compass, which is really a tiny magnet, always aligns itself such that its north pole points toward Earth's geographic north pole. Electrostatic and magnetic forces are related. A charged particle that is in motion creates a magnetic field. So an electric current made up of many moving charges produces a magnetic field. An electric field can be used to create an electromagnet. Summary. Magnets are objects made of certain materials such as iron, nickel, or cobalt. Magnets can exert forces on other magnets and objects that contain iron, nickel, or cobalt. Magnetic forces are both attractive and repulsive. Magnets can exert forces over other objects without touching because of the magnetic field surrounding it in 3 dimensions. All magnets have north and south magnetic poles. The strength of the magnetic field is stronger at the poles and decreases as the distance between the magnets is increased. Stop and check. What happens when two like poles of a magnet move toward each other? What happens when two opposite poles of a magnet move toward each other? How is the strength of a magnet related to distance? When one magnet exerts force on another magnet, the magnets do not touch. How do the magnets interact? Section 3. Gravitational force. You are probably familiar with Earth's gravitational force. This force pulls you toward the center of the planet. It prevents you and everything else on Earth from flying out into space as the planet spins on its axis. The gravitational force between Earth and the Moon keeps the Moon in orbit around the Earth. It can also pull objects that are above Earth's surface, from skydivers to asteroids, toward the center of the planet. There is a gravitational force between the Sun and all of the planets, moons, asteroids, and other objects that move around it in orbits. What may come as a surprise to you is that every object that has mass, large or small, exerts a gravitational force on every other object that has mass in the universe. This force also acts without objects touching, but unlike magnetic and electrostatic force, gravitational force is only attractive. It is never repulsive. Like magnetic and electrostatic forces, this non-contact force involves fields. In the 3-dimensional space around each mass, there is a gravitational field. This field can be represented by arrows. The arrows always point towards the mass, because the force is always attractive. The gravitational field around the Earth can be represented with arrows. As you may have discovered in the simulation, the gravitational force of attraction between two objects depends on the amount of matter, or the mass, of the objects. The greater the total mass of the two objects, the greater the force between them. This force also depends on the distance between the objects. As the distance between objects increases, the force of attraction decreases. As the distance between them decreases, the force increases. Gravitational force depends on the mass of the two objects and the distance between them. Falling on Earth. In the video, you observed a feather and a bowling ball falling from the same height in a vacuum chamber. When the air was removed from the chamber, both items hit the ground at the same time. How is this possible? How is this possible? Imagine that you have two blocks. One block has a mass of 10 kilograms. The other has a mass of 1,000 kilograms. The boxes are falling with no air resistance. In the diagram, you can see the boxes drawn and arrows that show the net force of gravity acting on each box. 10 kilograms, gravitational force 100 newtons. 1,000 kilograms, gravitational force 10,000 newtons. Review Newton's second law of motion. This law relates to force, mass, and acceleration. A equals F net divided by m. If you compare the ratio of the force to the mass for each box, you will see that each box accelerates at 10 meters per second squared. The more massive box experiences a greater force of gravity than the less massive box. However, the ratio of force to mass is the same for each box. Since both boxes have the same value for acceleration, they hit the ground at the same time. Comparing forces: electrostatic, magnetic, and gravitational. Electrostatic and magnetic forces are stronger than gravitational force. For example, the electrostatic force between a charged balloon and a wall is gigantic compared with the gravitational force between the two. But in our everyday experience, we feel that gravitational force is stronger. Why? Just as electrostatic forces are stronger, the more charge you have, the gravity is stronger with more mass. And we feel Earth's gravity as strong because the mass of the entire Earth is huge compared with the mass of ordinary objects. Now let us consider distance. With electrostatics, more distance means less force. If you move a balloon away from the wall, it is now many times farther from the wall than it was when they were in contact, and the force is small. It seems that if the force of gravity is constant, it does not get smaller as you get farther away, right? Wrong. With gravity, the distance that matters is the distance to the center of the Earth. Compared with that, if you climb to the top of a ladder, for example, you are pretty much the same distance from the center of the Earth as your friend who is still standing on the floor. So why can't we have a strong electrostatic force on a planetary scale? Imagine you wanted to make a planet entirely out of protons, positive charges. That would make a huge electric field and completely control the motion of any charged object in the area. The problem with that is that every proton in the planet would be repelling every other proton, and the planet would explode. Because gravity is always attractive and never repels, it can build up huge forces even though it is fundamentally weak. Summary: all objects are attracted to other objects by gravitational force. The strength of the gravitational force between two objects depends on the mass of the two objects. The greater the total mass of the two objects, the greater the force between them. The strength of the gravitational force also depends on the distance between the two objects. As the distance between objects increases, the force of attraction decreases. As the distance between objects decreases, the force increases. Stop and check. What is meant by gravitational force? When one mass attracts another mass through gravitational force, the masses do not have to be in contact. How does this happen? What does the strength of gravitational force depend on?